Good day, everyone. We are going to discuss chlor-alkali industries. First, we'll begin with its brief background, followed by its history, then most common products, and lastly, its manufacturing processes. For its brief background, one of the most significant heavy chemical industries produces soda ash, caustic soda, and chlorine soda. The manufacturing of chlorine, caustic soda, and other related compounds are called the chlor-alkali industry. The industry is essential to several fields, including manufacturing, water treatment, medicines, agriculture, and plastics. Electricity and salt are the two primary raw materials in the chlor-alkali industry. To create chlorine gas, caustic soda, and hydrogen gas, the industry uses an electrolysis procedure known as the chlor-alkali process. In the chlor-alkali process, salt is dissolved in water to make a brine solution. The next step is electrolysis, which involves passing an electric current through the brine solution. With this method, sodium chloride is divided into three products: caustic soda at the anode, caustic soda at the cathode, hydrogen gas at the anode, and chlorine gas as a byproduct. Many industrial applications make use of these goods. The vast majority of soda ash, caustic soda, and chlorine available are used in the production of fibers in plastics, glass, petrochemicals, pulp and paper, fertilizers, explosives, solvents, and other chemicals. The manufacturing of PVC polymers or polyvinyl chloride polymers, bleaching agents, and chemical intermediates are only a few of the many applications for chlorine gas. Strong bases like caustic soda are often employed in the making of pulp and paper, soap, textiles, water treatment, and alumina extraction. Both as an energy source and in several chemical reactions, hydrogen gas is employed. Since there are so many different uses, chlorine and alkalis are used to produce almost every consumer goods that can be purchased in the market currently. To increase productivity and environmental sustainability, the chlor-alkali sector has used technological innovations and process improvements. The sector has taken steps to reduce the environmental effects of its activities, including cutting back on mercury emissions, increasing energy efficiency, and looking into more environmentally friendly production techniques. Overall, the chlor-alkali industry supports a variety of sectors by providing vital chemicals for manufacturing and industrial processes, and by modifying to assure sustainability and environmental stewardship. The history of the chlor-alkali industry. The present synthetic process for the manufacture of soda is the solvay process. In 1773, before this method was developed, the Leblanc process was in universal use. It was based on roasting salt cake with carbon and limestone in a rotary furnace and subsequent leaching of the product with water. The crude product of the reaction was called black ash. It was leached cold, whereupon some hydrolysis of sulfides took place. These were changed to carbonate by treatment with the carbon dioxide-containing gases from the black ash furnace. The resulting sodium carbonate solution was concentrated to obtain crystalline sodium carbonate, which was then dried or calcined. No Leblanc process plant was ever built in the United States. In 1799, the first patent connected with the industrial use of chlorine is dated, a quarter century after its discovery, and it was used for bleaching. Chlorine was made from hydrochloric acid by the Deacon process, which does not have a satisfactory equilibrium. It was given by the chemical equation 2HCl plus 1 of O2 yields H2O plus Cl2. The Weldon process was also used. It conducted the oxidation of HCl with expensive manganese dioxide. In 1861, Ernest Solvay began developing the ammonia soda process. At first, this method had great difficulty competing with the older and well-established Leblanc process, but in a few years, the Solvay process reduced the price of soda ash almost by one-third. In 1890, the electrolytic production of caustic soda was known in the 18th century, but it was not until 1890 that caustic soda was produced for industrial consumption. Until shortly before World War I, the amount of caustic soda sold as a co-product of chlorine from the electrolytic process was almost negligible compared with that made from soda ash by lime causticization. In 1915, after a struggle during the producers of Leblanc soda used price cutting to attempt to stifle competition, the ammonia soda process completely displaced the Leblanc by 1915. In 1940, however, electrolytic caustic began to exceed lime soda caustic. In 1962, the lime soda caustic had almost disappeared. By 1982, the Solvay process continues to be of interest in Europe and countries without deposits of natural sodium carbonate. But by 1982, only one Solvay plant continued to operate in the United States. It is kept alive by low install costs and high freight rates. Natural soda from the Wyoming deposits now dominates the domestic market and has a brisk export trade. Caustic soda was originally made by batch-wise causticization of Leblanc soda ash with lime. It is given by the chemical equilibrium Na2CO3 plus CaOH2 yields 2 NaOH plus CaCO3. Depending upon the fact that calcium carbonate is almost insoluble in a caustic solution. The development of high-capacity direct current electrical generating equipment toward the end of the 19th century made the causticization process obsolete, and by the middle of the 20th century, more than 99% of the world's chlorine was produced by the electrolytic process.
These are the common uses that is associated with the industry. First is sodium hydroxide. So it is also known as caustic soda. And sodium hydroxide is a versatile and widely used industrial chemical, and it is used in various applications such as chemical manufacturing, pulp and paper production, water treatment, detergent production, petroleum refining, and many other industries. Next is chlorine. Chlorine gas is a highly reactive and powerful disinfectant. It is used for water purification, water treatment, swimming pool sanitation, and as a raw material for the production of various chemicals, including PVC, chlorinated solvents, and bleach. The next one is hydrochloric acid. Hydrochloric acid is a strong acid produced as a co-product during the chlor-alkali process. It is used in numerous applications such as metal picking, pickling, pH adjustment in water treatment, food processing, and chemical synthesis. The next is sodium hypochlorite. Sodium hypochlorite is commonly known as bleach. It is produced by reacting chlorine gas with sodium hydroxide, and it is widely used as a disinfectant, bleaching agent, and in the production of household cleaning products. Next is hydrogen gas. Hydrogen gas is a byproduct of the electrolysis process during chlor-alkali production. It has various applications, including being used as a fuel in the production of ammonia and in industrial process such as hydrogenation. Next is potassium hydroxide. In some variations of the chlor-alkali process, potassium hydroxide is produced instead of sodium hydroxide. Potassium hydroxide, also known as caustic potash, has similar applications to sodium hydroxide, and it is used in industries such as soap and detergent manufacturing, food processing, and pharmaceuticals.
Now I'm going to discuss the manufacturing processes. The manufacturing of soda ash. The preparation of soda ash is generally done using one of four processes: the Leblanc process, the dual process, the Solvay process, and the electrolytic process. Soda ash is a weak acid that is slightly soluble in ethanol and insoluble in alcohol. One of the important applications of this compound is as a water softener. Soda ash is typically prepared with the help of the Solvay process. In the Solvay process, ammonia and carbon dioxide are passed into saturated solution of sodium chloride. This triggers certain chemical reactions, resulting in the formation of sodium hydrogen carbonate. This compound is only very slightly soluble in the presence of sodium ions. Therefore, the sodium hydrogen carbonate is almost completely precipitated. It is then removed via the process of filtration and subsequently ignited in order to produce soda ash. Now let's move on to the manufacturing of caustic soda. Sodium hydroxide solutions are produced by three different technologies. First is the mercury cells, second membrane cells, and third is the diaphragm cells. Each of the processes utilizes sodium chloride salt as the primary raw material. Electrolytic splitting of salt results in products like chlorine and sodium ion. In the mercury cell process, saturated brine voyages down a steel through roughly 15 meters in length and 1 meter wide between a streaming film of mercury and titanium plates. Direct current is connected between the anode and cathode. Chlorine freed at the anodes gathers above the brine and is begun as hot, wet, and corrosive gas. Diaphragm cells processes utilize asbestos or alternative substitutes to asbestos to separate the co-product sodium hydroxide and chlorine. The production of 50% NaOH occurs primarily outside of the electrolytic cell. The diaphragm cell produces a very weak cell liquor that contains 12 to 14% by weight NaOH and the constant volume of NaCl salt. The cell liquor is subsequently evaporated in a 3 or 4 effect evaporation method to a final nominal concentration of 50% NaOH by weight. The surplus salt is precipitated and filtered through the evaporation method for the subsequent reuse or recycle. This method produces the lowest quality of electrochemical NaOH solution. And for the last process, the membrane cell method utilizes a selective membrane that separates the chlorine and sodium ions. The membrane permits the sodium ion to migrate across the membrane where areas, keeping the chlorine gas and salt solution in a compartment on the opposite facet of the membrane. Sodium ion is reacted with refined water as within the mercury cell to provide the caustic soda. Evaporation is employed as within the diaphragm method. To lift the concentration up to the nominal 50% weight solution, the salt concentrations are not targeted as considerably during this evaporation method, attribute to the selective diffusion nature of the membranes as well as the reduced quantity of evaporation needed during this method as opposed to the diaphragm evaporation. The caustic soda produced by the membrane cell process is most typically brought up as a membrane grade. It conjointly contains a growing acceptance as a rayon-grade product in all areas outside of rayon fiber production. Now let's talk about the manufacturing process of chlorine. Chlorine is an important industrial chemical. Chlorine is manufactured by the electrolysis of sodium chloride solution using a diaphragm cell and the membrane cell. Both cells rely on the same underlying chemistry but differ in detail. The diaphragm is made of porous mixtures of asbestos and polymers. The solution can seep through it from the anode compartment into the cathode side. Notice that there is a high level of liquid on the anode side that makes sure that the flow of liquid is always from left to right, preventing any of the sodium hydroxide solution from finding its way back to where chlorine is being produced. The membrane is made from polymer which only allows positive ions to pass through it. That means that only the sodium ions from the sodium chloride solution can pass through the membrane and not the chloride ions. The advantage of this is that the sodium hydroxide solution being formed in the right-hand compartment never gets contaminated with any sodium chloride solutions, the sodium chloride solution being used as to be pure. It is contained any other metal ions. This would also pass through the membrane and so contaminate the sodium hydroxide solution.
So in general, all chlor-alkali reactions include three reactions: chlorine evolution reaction or CER at the anode, hydrogen evolution reaction HER at the cathode, and a sodium hydroxide generation in the electrolyte. The figure shown is a chlor-alkali electrolysis cell. The chlor-alkali electrolyzer is mainly composed of three parts: anode, cathode, and ion exchange membrane. If chlorine and the alkali hydroxide are to be the final product, cell design must keep them from mixing. Many ingenious designs have been invented for practical cells. At the present, three types dominate the industry, as mentioned before: the diaphragm cell, the membrane cell, and the mercury cell. Although the energy consumption of the state-of-the-art chlor-alkali electrolyzers has been greatly reduced with technological progress, all of its structural parts still need to be further optimized. So seen in the figure here is the solvay process, which uses salt, limestone, and coke or natural gas as its raw materials and uses ammonia as a cyclic reagent. Its success depends upon the fact that ammonia, carbon dioxide, and water in the proper proportions react to form ammonium bicarbonate, which reacts with sodium chloride to form sodium bicarbonate, which is relatively insoluble in the solution used and can be filtered out and roasted to form soda ash. The ammonium chloride formed is converted back to ammonia by reaction with lime, the calcium chloride thus formed being the principal pollutant from the process. To be able to reduce or eliminate this pollutant, carbonation is used, which converts the carbonate present to bicarbonate, which is then flushed of brine salts, dried, and heated. This drives off the carbon dioxide, which is reused. Additional carbon dioxide is recovered from the boiler plant flue gas by absorption with monoethanolamine solution.